This tutorial is going to walk you through a basic Enercalc design, and we are going to be working out of the Steel textbook for example 9.1. We'll put that into Enercalc. So when you open Enercalc, it's going to ask you if you want to start a new project. On this one I called it tutorials, and I'm going to put all of my tutorial calculations in just one Enercalc file. That's one of the great things about Enercalc, is that you can do multiple calculations in just one file. So you'll want to select calculations and add. There's a lot of things to pick from, and if it's hard to pick from this list, you may look at narrow your selections, and we're going to go to steel, and we just want a plain steel beam. Once Enercalc opens, the most important thing will be to just read every single button that they give you an option for and think about what you want for every single option. So starting out in the description, this is going to be example 9.1 out of the textbook. The more description you can add, usually the better it is. We're going to pick either ASD or LRFD. We can do LRFD first. We know that our steel, based on the book example, said FY is 50, so that looks right. We know E for steel is 29,000 KSI. Again, we know that it's a steel beam, and then on the compression side, we want to know if it's in zone 1, 2, or 3. This says that it's laterally braced, and so that means the compression side is fully braced in this example. The next thing to look at too is going to be that CB value. Is the CB value always 1.0? The CB value comes from table 3.1 in the AISC code. This beam has uniform loads and is fully braced. So for this example, for simply supported uniform load, we'll just have it automatically calculate. If you know you want to call CB always equal to 1, you can check this box. Otherwise, we'll just leave it to where it automatically calculates. So the next thing that you'll do is go to your beam span data. Our example says the beam is 21 feet long. This is if you want to put a deflection limit in, L over 360, L over 180 for total load. If you're going to have weak axis bending, you'll want to check this box, but typically beams will bend around the x-axis, so we can leave that open. If you know what size your beam is, and we do, you can go in and actually pick your beam size in here. We're going to have a W21 by 44. You'll notice that it puts all of the properties in. This should line up with your AISC code. If you don't know what size the beam needs to be, you can click on the design button at the end after your loading is in, and it'll design the member for you. On our span loads, there's a few things we need to do. We're going to add the beam self-weight, and you'll notice when you start putting loads on, it's going to give you the ratio of how stressed it is. So with the beam weight alone, on a simply supported 21-foot span, we're at about 1% of the allowable stress that you can put into the beam. It's going to give you your MU. You'll remember that MU is your moment that's actually from factored loading, and your phi MN is going to be your factored strength that's allowed for this beam on that span with your bracing. We're also going to add a dead load, a uniform dead load. You'll notice the units are in kips per foot, which is what the problem gave it to us in. So we're going to put 1 kip per foot on dead load. We're going to put 3 kips per foot in on live load. And we're going to add that load in. You'll see that it shows up here, full uniform, 1 for dead, 3 for live. You can also double check your sketch button, and it should show you 1 for dead, 3 for live, 21-foot span, beam size, simply supported. Just a couple of different things that you can see here. You'll notice that this is 93% stress now with these loads on. So one thing that we can do, because this is the basic question that your book is asking, it says check the beam. Basically, is it okay? It's an analysis problem. So is the compact and brace section shown strong enough? For LRFD, yes it is. Right now we're showing it's only 93% stressed. So a couple of things you can check, again from your book, is your moment that they're saying is on your beam is 333.5 kip feet. You'll see over here the moment applied is 333.7. So it's a little bit different, but overall very, very close. Your capacity for LRFD, that would be your phi mn, is going to be 358 kip feet. On Enercalc, it gives 357.75, very, very close to 358. And what that's doing on your 93% is it's giving you a ratio of your strength as compared to your load, or load divided by strength. So if you take 333.67 divided by 357.75, then you should get this 0.93 number. It's also going to tell you your downward deflection, any upward if you have it, a total deflection with your dead and live load combined. It'll give you your support reactions. These are your shear numbers on how much shear stress is included. And then a few other things that you may want to look at is your load combinations. It's going to give you all of your LRFD load combinations here. And you can tell whether you want each one to actually be checked or not. It's also going to tell you down here the load combination that is controlling the design. And you can also look at the diagrams. This is going to be for all of your load combinations at once, your moment diagram, your shear diagram, and your deflection diagram. But overall, this calculation matches up very closely between the moment applied and the allowable moment as to what your book gives you. If you want to go back into your general and pick ASD, you'll see it recalculate, you'll see your load combinations change, and again, this shows yes, it's okay because it's only 93% stressed. Remember that even if it gets to 99% stressed, this is a factored load and a factored reduced strength. So we can go all the way up to a 1.0 here before the beam is not okay.